In an earlier video, we saw that when carbon is bonded to 4 atoms, we had an sp² hybridization with a tetrahedral geometry and an ideal bond angle of 109.5 degrees. If we look at one of the carbons in ethene, so let's say this carbon right here, we don't see the same geometry. So the geometry of the atoms around this carbon happens to be planar, and so actually this entire molecule is planar. So you can think about all of this in a plane here. And the bond angles are close to 120 degrees, so approximately 120 degree bond angles. And this carbon that I've underlined here is bonded to only 3 atoms, so a hydrogen, and a carbon. And so we must need a different hybridization for each of the carbons present in the ethylene molecule. And so we're going to start with our electron configurations over here, the excited state, right? So we have carbon's 4 valence electrons represented, so 1, 2, 3, and 4. And in the video on sp³ hybridization, we took all 4 of these orbitals and combined them to make 4 sp³ hybrid orbitals. In this case, we only have a carbon bonded to 3 atoms, so we only need 3 of our orbitals. So we're going to promote the s orbital. So we're going to promote the s orbital up, and this time we only need 2 of the p orbitals, so we're going to take one of the p's and then another one of the p's here. That is going to leave one of our p orbitals unhybridized, so each one of these orbitals has 1 electron in it like that. And this is no longer an s orbital. This is an sp² hybrid orbital, right? This is no longer a p orbital. This is an sp² hybrid orbital, and same with this one, an sp² hybrid orbital. We call this sp² hybridization. So let me go ahead and write this up here. Let's use a different color here. So this is sp² hybridization, because we're using 1 s orbital and 2 p orbitals to form our new hybrid orbitals. And so this carbon right here is sp² hybridized, and same with this carbon. All right, so notice that we left a p orbital untouched, so we have a p orbital unhybridized like that. In terms of the shape of our new hybrid orbital, let's go ahead and get some more space down here. All right, so we're taking 1 s orbital. We know s orbitals are shaped like spheres. We're taking 2 p orbitals. We know that a p orbital is shaped like a dumbbell. All right, so we're going to take these orbitals and hybridize them to form 3 sp² hybrid orbitals, and they have a bigger front lobe and a smaller back lobe here like that. And once again, when we draw the pictures, we're going to ignore the smaller back lobe. All right, so this gives us our sp² hybrid orbitals. In terms of what percentage character, right, we have 3 orbitals that we're taking here, and one of them is an s orbital. So 1 out of 3 gives us 33% s character in our new hybrid sp² orbital. And then we have 2 p orbitals, right? So 2 out of 3 gives us 67% p character. So 33% s character and 67% p character. So there's more s character in an sp² hybrid orbital than in an sp³ hybrid orbital. And since the electron density in an s orbital is closer to the nucleus, right? So if we think about the electron density here being closer to the nucleus, that means that we can think about this lobe right here being a little bit shorter, with the electron density being closer to the nucleus. And that's going to have an effect on the length of the bonds that we're going to be forming. All right, so let's go ahead and draw the picture of the ethylene molecule now. So we know that each of the carbons in ethylene, so just going back up here to emphasize the point, each of these carbons here is sp² hybridized. That means each of those carbons is going to have 3 sp² hybrid orbitals around it and 1 unhybridized p orbital. So let's go ahead and draw that. All right, so we have a carbon right here, and this is an sp² hybridized orbital. So we're going to draw in, there's 1 sp² hybrid orbital, here's another sp² hybrid orbital, and here's another one. All right, we go back up to here, and we can see that each one of those orbitals, let me go ahead and mark this, each one of those sp² hybrid orbitals has 1 electron in it. So each one of these orbitals has 1 electron. I go back down here, and I put in the 1 electron in each one of my orbitals like that. All right, and I know that each of those carbons is going to have an unhybridized p orbital here. So an unhybridized p orbital with 1 electron too. So let me go ahead and draw that in. So I'll go ahead and use a different color. So we have our unhybridized p orbital like that, and there's 1 electron in our unhybridized p orbital. All right, so each of the carbons, right, was sp² hybridized. So let me go ahead and draw the dot structure right here again so we can take a look at it. All right, the dot structure for ethylene. All right, so let's do the other carbon now. So the carbon on the right is also sp² hybridized. So we can go ahead and draw an sp² hybrid orbital, and there's one electron in that orbital, and then here's another one with one electron, and then here's another one with one electron. All right, and this carbon, being sp² hybridized, also has an unhybridized p orbital with one electron. So we go ahead and draw in that p orbital with its one electron. We also have some hydrogens, right? So we have some hydrogens to think about here. So each carbon is bonded to two hydrogens. Let me go ahead and put in the hydrogens. The hydrogen has a valence electron in an unhybridized s orbital. So I'm going ahead and putting in the s orbital, right, and the one valence electron from hydrogen, like this. All right, when we take a look at what we've drawn here, all right, we can see some head-on overlap of orbitals, which we know from our earlier video is called a sigma bond. Right, so here's a head-on overlap of orbitals, so that's a sigma bond. Here's another head-on overlap of orbitals. Right, the carbon-carbon bond, here's also a head-on overlap of orbitals, and then we have these two over here. And so we have a total of 5 sigma bonds in our molecule. So let me go ahead and write that over here. So there are 5 sigma bonds. Right, if I'm trying to find those on my dot structure, that would be this would be a sigma bond, this would be a sigma bond. One of these two is a sigma bond, and then these over here. So a total of 5 sigma bonds. And then we have a new type of bonding. Right, so these unhybridized p orbitals can overlap side by side. Right, so up here and down here we get side by side overlap of our p orbitals, and this creates a pi bond. So a pi bond, let me go ahead and write that here. So a pi bond is side-by-side overlap. Right, so there is overlap above and below this sigma bond here, and that's going to prevent free rotation. So when we're looking at the example of ethane, we had free rotation about the sigma bond that connected the two carbons, but because of this pi bond here, this pi bond is going to prevent rotation, so we don't get different conformations of the ethylene molecule. So no free rotation due to the pi bond. Right? When you're looking at the dot structure, one of these bonds is the pi bond, so I'm just going to say it's this one right here. Right? So if you have a double bond, one of those bonds is a sigma bond and one of those bonds is a pi bond. So we have a total of 1 pi bond, right, in the ethylene molecule. If you're thinking about the distance between the two carbons, right, so let me go ahead and use a different color for that. The distance between this carbon and this carbon, right, so it turns out to be approximately 1.34 angstroms, right, which is shorter than the distance between the two carbons in the ethane molecule. Remember, for ethane, the distance was approximately 1.54 angstroms. And so a double bond is shorter than a single bond, and one way to think about that is the increased s character, right? So this increased s character, right, means the electron density is closer to the nucleus, and so that's going to make this lobe a little bit shorter than before, and that's going to decrease the distance between these two carbon atoms here. So 1.34 angstroms. All right, let's look at the dot structure again and see how we can analyze this using the concept of steric number. So let me go ahead and redraw the dot structure. So we have our carbon-carbon double bond here and our hydrogens like that. If you're approaching this situation using steric number, remember to find the hybridization, we can use this concept. Steric number is equal to the number of sigma bonds plus number of lone pairs of electrons. So if my goal was to find the steric number for this carbon, right, I count out my number of sigma bonds. So that's 1, 2, and then I know in a double bond, one of those is sigma and one of those is pi. So one of those is a sigma bond. So I have a total of 3 sigma bonds. I have 0 lone pairs of electrons around that carbon. So 3 plus 0 gives me a steric number of 3. So I need 3 hybrid orbitals. And we've just seen in this video that 3 sp² hybrid orbitals form if you're dealing with sp² hybridization. So if you get a steric number of 3, you're going to think about sp² hybridization, 1 s orbital and 2 p orbitals hybridizing. All right, so that carbon is sp² hybridized, and of course this one is too. So both of them are sp² hybridized. Let's do another example. Let's do boron trifluoride, right? So BF3. If you want to draw the dot structure for BF3, right, you would have boron, and then you would surround it with your fluorines here, and you would have an octet of electrons around each fluorine. So I'll go ahead and put those in on my dot structure. If your goal is to figure out the hybridization of this boron here, right, so what is the hybridization state of this boron? Let's use the concept of steric number. So once again, let's use steric number. So find the hybridization of this boron. Steric number is equal to number of sigma bonds, so that's 1, 2, 3, so 3 sigma bonds, plus lone pairs of electrons, that's 0. So a steric number of 3 tells us this boron is sp² hybridized. So this boron is going to have 3 sp² hybrid orbitals and 1 p orbital, 1 unhybridized p orbital. So let's go ahead and draw that. So we have a boron here bonded to 3 fluorines, and it also is going to have an unhybridized p orbital. Now remember, when you are dealing with boron, it has 1 less valence electron than carbon. Carbon had 4 valence electrons. Boron has only 3. So when you're thinking about the sp² hybrid orbitals that you create, sp² hybrid orbital, sp², sp², and then 1 unhybridized p orbital right here. Boron only has 3 valence electrons. So let's go ahead and put in those valence electrons, 1, 2, and 3. So it doesn't have any electrons in its unhybridized p orbital. And so over here, when you're looking at the picture, right, this has an empty orbital. And so boron can accept a pair of electrons. So if you're thinking about its chemical behavior, right, one of the things that BF3 can do, the boron can accept an electron pair and function as a Lewis acid. And so that's one way in thinking about how hybridization allows you to think about the structure and how something might react. Right? So this boron turns out to be sp² hybridized. Right? So this boron here is sp² hybridized. And so we can also talk about the geometry of the molecule. Right? It's planar. Right? So around this boron it's planar, and so therefore your bond angles are 120 degrees. So if you had boron right here and you're thinking about a circle is 360 degrees. So if you divide a 360 by 3, you get 120 degrees for all of these bond angles. All right, in the next video we'll look at sp hybridization.